And let's move on to higher order derivatives. So the derivative of f of x is f prime of x. It is also what we call the first derivative. Now f prime of x itself can have a derivative which is f prime prime of x, which is the second derivative. And as I wrote here, the second derivative f prime prime of x, this is the rate of change of the rate of change. Because we said the rate of change is the first derivative, so the rate of change of the first derivative is the second derivative. Now, in order to, like, we can have a third derivative and like more, a fourth derivative in order to write the nth derivative of f. We either write the n in a superscript like this, or of course we can use Leibniz notation. Now, why is this useful? If position is our function, the first derivative of the position, let's say position s with respect to t, the first derivative of s of t is velocity. The second derivative of s of t is acceleration. Notice that acceleration is the second derivative of s of t, but it's the first derivative of velocity. Now, the third derivative of s of t is what we call the jerk function. Notice that the jerk function is the third derivative of s of t, but it is the first derivative of acceleration, and it would be the second derivative of velocity. Now, let us learn about implicit differentiation. So we use it when we can't solve for y, or when it is a bit complicated or maybe not really easy to solve for y. So let's say we will explain this with an example. So let's say x squared plus y squared equals to 25, and we are told to find dy dx. This is from page 211 in the book. So what we do in such a case is we first take the derivative of both sides. One thing to note that we are taking the derivative with respect to x. So we differentiate the x normally. So the derivative of x squared is 2x. We differentiated normally. However, when we get to a y, we start by differentiating it normally. So we write 2y because this is the derivative of y squared. However, we also have to multiply it by y prime, or by the derivative of y, because we are differentiating with respect to x and not with respect to y. And finally, the derivative of a constant is 0. So what we do after that is we solve for y prime. It is equal to negative 2x divided by 2y. I can cancel the 2's, which it becomes negative x over y. Let us now look at a different example. Suppose we have sine of x plus y equals to y squared cos of x. We would like to find y prime, or the derivative of y, and this comes from page 213 in the book. So, first of all, as I already said before, we take the derivative on both sides. So let's start with the left side, derivative of sine of x plus y. First of all, this is the chain rule, so I take the derivative of what's outside. Derivative of sine is cos. I evaluate it at what is inside, so I evaluate this derivative at x plus y, and then I take the derivative of x plus y. Now let's move to the right side. The derivative of y squared cos of x. These are two terms that are multiplied, so I use the product rule. So I keep the first term the same, I multiply it by the derivative of the second term, and then I add this to the derivative of the first term times the second term. Let's go back to the left side, cos of x plus y times the derivative of x plus y. Again, we take the derivatives of x normally, so the derivative of x is 1. However, when it comes to the derivative of y, first we take it normally, so the derivative of y is 1, but we also multiply it by y prime. And this is equal to, on the right hand side, y squared times the derivative of cos of x, so negative sine of x, plus the derivative of y squared, so 2y, and we multiply it by y prime times cos of x. And now what I do here is I need to solve for y prime. So I isolate everything that has y prime on one side of the equation. So I have y prime in here, and the y prime in here. Maybe before isolating it, I can maybe expand a bit. So if I expand the 1 and the y prime, I will get cos x plus y times 1, which is cos of x plus y, plus y prime times cos of x plus y, which is equal to y squared times negative sine of x plus 2y y prime cos of x. Now everything that has y prime, I will take it to the left side. So on the left side, I now have y prime cos of x plus y. And I take this to the left side, minus 2y y prime cos of x. On the right side, y squared times negative sine of x. And I take this to the right side, minus cos of x plus y. Now let's factor y prime. I will get cos of x plus y minus 2y cos of x. This is equal to y squared times negative sine of x minus cos of x plus y. Now let's solve for y prime. I get y squared times negative sine of x minus cos of x plus y. All of this divided by cos of x plus y minus 2y cos of x. And this is my answer. And let us move to another example. So suppose that x to the power of 4 plus y to the power of 4 equals to 16, and we would like to find y prime prime, or the second derivative. So again, we will use implicit differentiation. We will differentiate the left side and the right side. So derivative of x to the power of 4 plus y to the power of 4. This becomes, for x to the power of 4, we drop the power, so it becomes 4x to the power of 4 minus 1. So 4x to the power of 3. Same for the y, it becomes 4y to the power of 3, except since we're differentiating with respect to x, when we differentiate y, don't forget to write y prime after it. And on the right side, this is equal to 0. Now we solve for y prime. This is equal to negative 4x cubed divided by 4y cubed. We cancel out the 4's. This gives us negative x cubed divided by y cubed. Now let's find the second derivative, and the second derivative is the first derivative. So it's the derivative of the first derivative. So it's the rate of change of the rate of change. And now we want to find the derivative of negative x cubed divided by y cubed. So this we can use the quotient rule because this is a fraction. So the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. So let's continue. What's the derivative of negative x cubed? We drop the power, so we drop the negative 3, and instead of x cubed, we have x squared. And what's the derivative of y cubed? Again, we drop the power. Instead of y cubed, we have y squared, and whenever we differentiate y, don't forget to write y prime after it. And now let's simplify a bit. So this becomes y cubed times negative 3x squared. What we will do here, so minus negative x cubed times 3y squared. Instead of the y prime, we already found what y prime is, so we can replace it. We can write negative x cubed divided by y cubed in here. So now let's simplify a bit more. So this leaves us with, on the left side, or at the start of the numerator, negative 3x squared times y cubed. So here we have a minus times a minus becomes a plus times a minus becomes negative. So minus 3, which is here, x to the power of 3 times x to the power of 3 is x to the power of 6, and y squared divided by y cubed is y. So this leaves us with these two fractions. So we can find the common denominator and add them up. So we can multiply the denominator of the first fraction by y and the numerator by y. So we get negative 3x squared times y power 4 minus 3x to the power of 6 divided by y, all of this divided by 6. And now I can drop this y down to the denominator of the entire thing. So I get negative 3x squared times y to the power of 4 minus 3x to the power of 6 divided by y to the power of 7. And then I can factor the 3x squared, the negative 3x squared, I factor it out, and I'm left with x power 4 plus y power 4, all divided by 7. And now comes the magic. We got x power 4 plus y power 4, which is in fact what we had at the start, which is in fact 16. So we replace it by 16 in here. And now we have negative 3x squared times 16 divided by y to the power of 7, which is negative 48x squared divided by y to the power of 7. And this is our second derivative. This is the answer. And now we will move on to learn what we call logarithmic differentiation. We will learn again with an example. Suppose we have y equals to x to the power of x. This is from page 221. We would like to find the derivative of y, so we are looking for y prime. So we differentiate, before differentiating each side, because I mean, how do we differentiate x to the power of square root of x? This is something new, so we will learn it now. So what we do, first of all, is we take the ln of each side, and when this happens, using log rules, we can drop the power and get square root of x, ln of x. And now we differentiate each side. So the derivative of ln of y, this is 1 divided by y times y prime. And the derivative of square root of x ln of x. So the derivative, this is a product, so we do square root of x times the derivative of ln of x plus the derivative of square root of x times ln of x. So on the left side we have y prime over y is equal to, on the right side, square root of x. The derivative of ln of x is 1 over x. Now the derivative of square root of x, which can be written as x to the power of half, we drop the power and we subtract 1 from the exponent, so half minus 1, which is negative half. All of this times ln of x. And now we solve for y prime. It is equal to y times square root of x divided by x plus, I will slightly rewrite this here, I will simplify it a bit, I will write it as ln of x divided by 2 square root of x. And now instead of this y right here, what is y? Y is x to the power of square root of x. So I write here x to the power of square root of x, and I copy the entire thing from here. So the same thing, I write square root of x divided by x plus ln of x divided by 2 square root of x. And this is our answer. And let's look at this example, y equals to cos of x to the power of x. This comes from the page 224 in the book. So again, when we have x to the power of x, so x in the base and x in the exponent, we can use logarithmic differentiation. So we take the ln on both sides, and then we drop the power because we can use log rules. So we drop the power, it becomes x ln times ln of cos of x. So then we differentiate each side, and when we differentiate ln of y, it's 1 divided by y, and don't forget to multiply it by y prime. And then we look at the right side, we want to differentiate it. This is x times ln of cos of x. So this is a product. We are multiplying x by another term. So we keep the first term the same, we multiply it by the derivative of the second term, and then we take the derivative of the first term and we multiply it by the second term. So let's compute these derivatives. The derivative of ln of cos of x. So this is the chain rule. So I do the derivative of what's outside. So the derivative of ln is 1 divided by x. I compute it at what is inside. So I compute 1 over x, so it becomes 1 divided by cos of x, which is what I can see here. And then I multiply this by the derivative of what is inside. So I multiply it by the derivative of cos of x, which is negative sine of x. Let's look at the other derivative we have to compute here. The derivative of x is 1. So this is what we are left with, x times negative sine of x divided by cos of x plus ln of cos of x. And here, don't forget, we will solve for y prime, so the y, we can move it to the other side. And y is cos of x all to the power of x. So this is why we wrote it right here, and we keep the rest the same. Finally, we have this additional problem for anyone who would like to challenge themselves more. So I will not go over it in details, but feel free to pause the video if you would like to solve it. And now I will show you the answer. This is f prime of x. Keep in mind that this is a quotient, a division, so we will use the quotient rule. And we have here, this is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. And keep in mind that the numerator itself is a product, so to find its derivative, we have used the product rule in here. And the denominator as well, it's a product, so again, to find its derivative, we use the product rule as well.